Okay, so today we're going to talk about modeling with exponential functions. The only two assessments left for the semester are Project 5, which is due this Friday. And it will very much help you study for the final. Hint. I will give it back to you on Monday, the review day. So if you want to use it as one of your 4 pages of notes that you can bring to the final, you can do that. Yeah, so yeah, you can bring 4 pages to the final. So if you saved your notes from the first 3 tests, that was the idea, that you could just reuse those, and then you can have 1 more page to add for any additions. So yeah, we'll talk more about the final each class, but it will be approximately the same-ish length as all your other tests, like maybe 1 more question, but it's 2 hours, and yeah, we can talk about it more as it gets a little bit closer. But everything start to finish, it is cumulative. And at the back of the packet that you're working out of right now, there's a review study guide for the final exam. Sorry. Sure. Yeah. So cumulative sometimes in the class feels like, all right, like a couple questions from each thing, or it feels like really tough questions that have like all the steps, like because you go through each step. Oh. One overall question. How do you usually? I would say it's more a little bit on each topic. Yeah, okay. There are some themes, like the theme of this class is functions, right? So there's definitely a theme of like every question sort of refers to functions. And all the things that you should be able to do with functions, like compose them, find their inverse, find their domains and ranges, like there's lots of different kinds of functions, but for all of them you need to be able to do those things. So it is kind of one informs the other, and you'll also have, it will be a specific question. Yeah. And if you look at the practice problems for the final, those will give you a really good flavor of what it'll look like. Sure. Sorry, what? Oh yeah, I just haven't gotten to that yet. I'll get it to you for next class. Or you can come to my office and we'll look at my spreadsheet. Okay. Okay, so yeah, that's it. Project 5 coming up, final exam coming up. Okay, so let's go through some of these preview exercises together so we can kind of remind ourselves of important concepts that we're going to use today. So I have a formula, A equals 10e to the negative 0.003 t, and it models the population of Hungary, which we're going to call A, t years after 2006. Anybody else not here? This is the kind of thing you guys should do before class. Okay. Okay, so A represents the population of Hungary, which we're going to measure in millions. T is going to represent years since 2006. So how would I find Hungary's population in 2006? Plug 0 in. So I could use function notation and write A of 0. That would be 10e to the negative 0.003 times 0, which is 10e to the 0, which is e to the 0 is 1. Yeah, so this is 10 million, right? So population, Hungary's population in 2006 is 10 million. How would I figure out for 2008? Plug it. Yes, but I meant to say 2007. Oh. You read my mind. So for 2007, you'd plug in a 1. So maybe I'll get my calculator out to do this one. So I do 10e to the negative 0.003 times 1. Oops, I'm missing a 0. So I get 9.97. And again, that's million people. So this is 06, 07, and to get 08, I'd plug in a 2. So I'll just replace that 1 with a 2. And in 2008, 9.94 million. And then 2009, I'd plug in a 3. 9.91. Okay. So look at this list, this sequence of populations. I've got 10, 9.97, 9.94, 9.91. Is the population going up or going down? Down, so it is decreasing. All right, so could I have known that it was decreasing just by looking at the formula? How? The negative exponent. Yeah, good. Okay, so here I've got a table and a scatter plot that show the annual retail sales for the Call of Duty video games from 04 to 2010. So based on the shape of the scatter plot, so if we just look at the scatter plot here, would an exponential, a logarithmic, or what was my other choice? Or a linear function be used to model that data? It's exponential, I think, because if you try to connect them with like a smooth curve as best you can, it definitely has that upward bend to it. So that looks like exponential. Although a line might not be bad, right? If I tried to draw a best fit line, that would also look pretty decent. But I think the exponential could get a little bit closer to all the points. Yeah. Right. So, right. Sales can't just keep going up and up forever and ever, right? Eventually, people are going to get sick of the Call of Duty video games and they're going to be old fashioned and people aren't going to buy them anymore. But both of these models have that same problem, right? The line and the exponential are both going to keep going up forever in terms of end behavior. So yeah, maybe you could either say that maybe these aren't good models, or maybe they're only good for a finite amount of time. All right, so today we're going to talk about exponential growth and decay and writing models for real life things that grow and decay exponentially. So with exponential growth and decay, they come in 2 equivalent forms. You can use a base of B or a base of E. So they are exactly the same. They model the same thing. A sub 0 always represents your initial quantity. So in both forms, A sub 0 is the same thing. That first number is your initial amount. And then you can either do times b to the t or times e to the kt. And for those 2 formulas to be the same, it would have to be that b to the t and e to the kt are the same thing, right? In order for these 2 formulas to be equivalent, those 2 pieces would have to be the same. And for those 2 things to be the same, b would have to equal e to the k, right? So for these 2 equations to be equivalent, b has to equal e to the k, or equivalently, k is the ln of b, right? If you just took that guy and solved for k by taking the ln of both sides, you get k is the ln of b. So b we call a growth or decay factor. When b is bigger than 1, you have growth. Between 0 and 1, you have decay. K, the exponent when you use the other form, is called the continuous growth or decay rate. So that word continuous is like a really special meaning. If you see that in a problem, you have to use the formula with the E in it or convert it to a B. When K is positive, growth, K negative, decay. All right, so let's look at an example. In the fall, there was this big Ebola outbreak. You guys remember? Yeah. So on September 3rd, there were estimated 3,902 Ebola cases recorded in West Africa. And between September 3rd and November 18th, the number of Ebola cases grew at a continuous growth rate. So you see that word continuous, and that tells you which formula they're talking about, of 1.252% per day. So I want to create two equivalent models, right? One that looks like this and one that looks like this. I'm going to write two different equivalent formulas for the West African Ebola outbreak. All right, so 1.252%. First, let's convert that to a decimal. What does that come out to? Yeah, you just move that decimal 2 to the left and you get 0.01252. So that's as a decimal. So I'm going to suggest we start with the model that they gave us a piece of. They gave us a k from e to the kt. So let's just write down that model. F of t is a sub 0 times e to the kt. They gave us k, right? So an a sub 0 is your initial amount. What's that going to be? 3,902. 3,902. E to the k, which is 0.01252 t. And this is per day. So if you wanted to use this formula, t is in days. Okay. All right, now I would like to write an equivalent formula that looks like the other form. A sub 0 times b to the t. And if I know k, how could I figure out b? K is the ln of b, but k is the one I know, and I would like to know b. So I could use b equals e to the k, right? Just do e to the k and you get b. In the calculator, yeah. So I would do e to the 0.01252. So I would write off to the side here, b is e to the k. So b is e to the 0.01252. So b is approximately e to the 0.01252. And I get 1.0126. Does that number for b make sense? I did e to the 0.01252. E is the number 2.718, blah, 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 blah. So look at in the continuous growth formula, k was positive, right? Which indicates growth. In order to have growth in this formula, what has to be true of b? Has to be bigger than 1. Yeah. And the number I came out with is bigger than 1. So at least that piece of it makes sense. So then I'm just going to plug in here. My a sub 0 is 3,902. And then my b is 1.0126 to the t. So I've got two formulas, right? They are completely the same. If I plug a number into one, I'll get the same thing as if I plug a number into the other. They are completely equivalent. So let's just see what happens. I want to represent November 18th is going to be day 83, right? That's 83 days after September 3rd. So we want to know how many Ebola cases does the model predict. So I go to my calculator. If I use this model, I have 3,902 times e to the 0.01252 times 83. And it says about 11,030 cases. Right? If I use my other model, I have 3,902 times 1.0126 to the 83. And I get almost the same number. Why did I come out just a teeny bit different? Rounding. Yeah, I rounded this 1.0126 a little bit. So either way, it comes out to approximately, oh, whoops, that's not what they asked me. So November 18th, so let's see, day 83. Both models give approximately 11,000, we'll just say 30, round to the nearest 10, 11,030 cases. But I'd like to make a prediction for December 5th. So how many days are there between November 18th and December 5th? 17. So we've got the 19th we already counted as day 83. So we've got 19, the 18th, you're right. So we've got 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 30 days has September, April, June, and November. Okay, then December 1, 2, 3, 4, 5. So I think 17, 17 days. All right, so I need to add 17 to 83. So that makes 100 days. 100 days after September 3rd. 100 days. So I want to use each of my models for 100 days and see what I get for December 5th. So I'm going to replace in each of my models, plug in 100 for T. So instead of an 83 here, I'm going to put a 100. And this model, the times B to the T model, gives me about 13,650. And my other model should be equivalent. Let's just double check. Instead of 83, I'm going to put 100. Oops. And 13,650 approximately. They're off by 2. Any questions? So generally, when I give you problems that are exponential growth, I won't make you write 2 models, right? You should use whichever model they give you the information for. If they say continuous growth rate, use the e to the k because you have the continuous growth rate. If they give you a growth factor or a percentage growth rate, use the other one because it's easier. All right, now we can also have exponential decay, also called radioactive decay. And the half-life is something that we often use to try to figure out how old something is. The half-life of a substance is the time required for 1/2 of the current amount to decay, to go away, to get broken down somehow. So we have 2 equivalent formulas, similar to before. 1/2 to the T over H, so we're going to have M0 times 1/2 to the T over H, or M0 to the negative RT. M0 is your initial amount, again, initial amount, the amount of stuff you start with. T is time, H is half-life, and R is called the continuous decay rate. So if they use that word continuous, jump immediately to this formula, the one with the E in it. If they say the half-life, they give you half-life, jump to the formula that has an H in it. You can convert between the two. They're equivalent, and R is the ln of 2 over H, and H is the ln of 2 over R. So I'm not going to derive where those come from, but if you needed to convert from one to the other, you could use those 2 formulas. All right, so we'll do quick example, and then you'll do some on your own. So the burial cloth of an Egyptian mummy, it's estimated to contain 59% of the carbon-14 it originally contained. So this is called carbon dating. Some carbon is radioactive and it decays with a half-life of 5,730 years. So every 5,730 years, half of it is gone. So we can tell how old something is by knowing how much carbon-14 it would have had when it was new and looking at how much it has now. So for example, an Egyptian burial cloth is probably made of cotton, and we know how much carbon-14 is in brand new cotton. And we say, okay, well, this piece of cotton that we found from ancient Egypt has 59% of the C14 that new cotton has in it. So they gave me half-life, right? So I should use the formula that has H in it. So M of T is M0 times 1/2 to the t over h. And we start plugging in the stuff they gave us. So they're saying right now, the amount of C14 we have, m of t represents the amount of C14, right? Is 59% of what we started with. So how much did we start with? 100%. So I'm going to put in 100 for M0 and a 59 for how much we have now. And then I copy my 1/2. And then T is the independent variable, so I'm going to leave it. And H is half-life, 5,730 years. And then we just want to solve for T. That will tell us how old this thing is. So it makes sense that T is the variable we're solving for. So now let's get a little practice with solving an exponential equation, which we learned how to do last class. The first thing is to isolate the exponential expression. So what should I do? Divide both sides by 100. So these hundreds cancel. And we have 0.59 is equal to 1/2 to the t over h. So, I'm sorry, h is a number. 5,730. All right, how do you get a variable out of an exponent? The inverse of what? Yeah, what's the inverse of an exponential? Logarithm. Yeah, you take the ln of both sides. So I'm going to take the ln of 0.59, and that equals the ln of 1/2 to the t over 5,730. So I just wrote ln of both sides. So the whole reason we take the ln is because we have this property of logarithms that lets us take the whole exponent and bring it down in front of the log. So the left side doesn't change at all. I have the ln of 0.59, and that's going to equal t over 5,730 times the ln of 1/2. So now you just have to have this mantra. LNs are just numbers, right? The ln of 1/2, that's just some number. I could type it into my calculator, it's just a decimal, right? And the ln of 0.59, that's also just some number. So if those were just numbers, this would not be a hard equation to solve, right? I just want to get the t by itself, so what should I do? Multiply by what? 5,730. So yeah, I'll do that first. Multiply both sides by 5,730. So on the right, the 5,730s cancel. And I have t times the ln of 1/2. And on the left, I have 5,730 times the ln of 0.59. And then what do I do to get the t by itself now? Divide by ln of 1/2. Okay, so my final answer, these cancel, and I'm going to have t equals 5,730 times the ln of 0.59 divided by the ln of 1/2. But if somebody asked you, how old is this Egyptian burial cloth? And you said 5,730 times the ln of 0.59 divided by the ln of 1/2, they'd probably punch you in the face, right? So you should type that into your calculator and give a decimal answer. All right, so 5,730 times the ln of 0.59, and then take the result and divide by the ln of 0.5. And we have 4,361. We'll just round to the nearest whole year. 4,362 years. Is that an answer that kind of makes sense for how old something from ancient Egypt might be? Yeah. Sure. Good. Any questions on that? All right. If I wanted to know the continuous decay rate of carbon-14, they gave me the half-life, right? And I have formulas that relate continuous decay rate to half-life, right? So I have half-life. I would like to know continuous decay rate, R. So R is just the ln of 2 divided by the half-life. So my continuous decay rate is just going to be ln of 2 divided by 5,730. So I get approximately 0.000121. Or as a percentage, 0.0121%. It comes out as a decimal, and then you can convert it to a percent if you want. Oh, sorry, I converted that without realizing you didn't know what I was doing. So that e to the -4, that means times 10 to the -4, and that means move the decimal place 4 to the left. So it's right after the 1, so I moved it 1, and then 2, 3, 4 places means I have to put 3 zeros there. Yeah, the calculator was saying I can't fit this whole number in the screen, so this is scientific notation. So that e to the -4 means move the decimal place 4 to the left. Okay, so we've been talking about exponential growth. Kieran, you suggested earlier that it's not sustainable, right? Thing like for the population of whatever that country was, I can't remember now. What is it? Hungary, yeah. It can't just keep going up forever. So we have this other model called a logistic growth model that takes into account the fact that in most growth situations, indefinite growth is not realistic. You can't just keep doubling every how often, right? So growth is always limited because of space and resources. And the logistic growth model is used to capture long-term behavior of a growing population. So I'm not going to ask you to do a lot of algebraic work with the logistic growth model, but I just want you to know that there is a formula that represents logistic growth. And logistic growth is characterized by an S-shaped curve that looks exponential at first, right? But then as we get closer and closer to what's called the carrying capacity of the environment, the population continues to increase, but slower and slower and slower until it approaches the carrying capacity. And then it just stays constant, which is a horizontal asymptote. Good. Very good. So the US Census Bureau is currently using a logistic model to predict world population in the future because it looks like somewhere in the 90 to 2000 range, we switched from this exponential growth where it's bending upwards to this more logistic growth where it's bending downwards. So somewhere here, we switched from that growing faster and faster and faster to still increasing, but increasing slower and slower and slower. Again, I won't ask you to do a lot of algebraic things with this model, but I just want you to know that it exists. Yeah. Okay, that's it. You can do some stuff on your own now.